All right, talking more about the fundamental theorem of calculus and connections to some other stuff that we've done. And this kind of goes along with our class starter that we just talked about. If you're given a function that represents a rate, so a lot of times it'll be done that way by a derivative, right? A derivative is a rate. It's a rate of change. Sometimes you might just get a regular equation, but it's an equation for a rate. Could be an equation that talks about how many miles per hour you're talking about. So it might be represented like, for example, velocity. It's not written as a derivative, but we know it's the derivative of position. Well, you can find the total change over time period from A to B by finding the area under the graph. Right? So the total change of whatever that function was by finding the area under the curve. So here are some examples. This first one's kind of like our class starter. Here, if we have the y-axis labeled in miles per hour, x-axis in hours, area under the curve, we're multiplying these things together basically, and we're getting miles per hour times hours. Our answer is going to be in miles. So it's going to be the change in miles from this time period to this time period. People per hour and hours, right? We multiply those, we get people. So it's going to be the change in people, or change in number of people over a time period. Miles per gallon times gallons, we're going to get miles. So kind of keep that in mind when we're looking at area under the curve. We're finding the total change of that original function. So to kind of, we looked at it kind of graphically there. Here we're looking at it using calculus. Here's our fundamental theorem of calculus. Definite integral from a to b of the derivative f of x dx is f of b minus f of a. Right? So this is our rate of change. This definite integral is the sum of all of that changing. And this shows us the change in that function. Alright, so the area under the graph of a rate from a to b equals the change in the original function from a to b. One of our more common ones that we'll see and kind of makes sense to us, because you've seen it a lot in the past, is with velocity and position. If we take the definite integral of velocity, that's going to equal s of b minus f of a. So the position at time b minus the position at time a. Right? So it's just the change in position from a to b. That's what the area under that curve is representing. Well, the fundamental theorem of calculus, we can kind of manipulate that to help us in certain situations also. If we just take this and solve for f of b, so we would add f of a to the other side, and I'm just going to kind of flip it over so that f of b is over here on the left, but we get f of b equals f of a plus the definite integral from a to b of that derivative. Well, that means f of b equals f of a plus the change in f from a to b. Right? So if we add that change to f of a, we're going to get to f of b. So this can work on a regular function too. I know I'm trying to connect it to like real life scenarios, but if we're just talking about a function, if we start at this y value and we add the change in the y value during this time, we're going to get this y value. So here are some kind of basic ones where we would do that. So for number one, we have our derivative. We have a value on the original function. We want to find another value on that original function. In the past, we would do like the antiderivative of this. We'd have a plus c. Then we'd plug these numbers in, figure out what c is to get the original equation. Then we could put 5 in. So that's one technique we could use. But this fundamental theorem of calculus kind of helps us and sets up a nice, easier way to do this. So let's look at this formula. And this is the formula that you're going to need to kind of know and remember. I mean, you already know and remember fundamental theorem of calculus, hopefully, or you should. This is just a slight variation of that, and just kind of knowing when to maybe use that. So for this one, we want to figure out f of 5, so that's like our f of b. All right, so f of 5 equals our f of a. This has to be something that we already know, like a value on the original function that we know. So that's going to be our f of 3. Plus the change in the function from 3 to 5. So this definite integral, this number is always going to be the same as this one. So these two are the same, and then this one is the same as the upper limit. And on the inside we have the derivative of f of x. So let's go ahead and fill in what we know. We know that f of 3 is 9. And here we're finding the definite integral from 3 to 5 of 3x squared minus 4x dx. Well, we could do this by hand, and I've had you practice that by hand in the past, but now I'm going to give you a shortcut. I know you're going to be mad at me because why didn't you give me the shortcut earlier? But you need to be able to do it by hand in certain situations as well, but we don't need to waste time doing it by hand every time. In certain situations you may still be called upon to do that, but now there's a way we can do this on our calculator. So do me a favor and take your calculators out. Alright, so with our calculator, if you go to math, which is right here below the alpha key, and scroll down to number 9, it says FNINT. Well, you're doing the definite integral of a function. That's what this is doing. Now, some of you with newer calculators, you're actually going to get an integral sign and you have to fill in the spot, so it makes it a little bit easier. But if you have an older one like me, kind of show you how to set it up. First thing we're going to put in here is the function we're taking the definite integral of. So we have 3x squared minus 4x. Of course, if you have an integral there, you're just putting it inside the integral. But if you're doing this, then you have to do comma x. If you have the integral, it has a d with a space there. You have to put the x in for the dx. That's kind of what this is doing here. Slow down, Speedy. All right, and then the next thing we're going to put in is the lower bound. So in our case here, it's going to be the 3, and then the upper bound. Hit enter, and that evaluates that definite integral for us. So we don't have to do like x cubed minus 2x squared, put 5 in, put 3 in, subtract it. Calculator's doing all that work for us. So be careful though, because where did I get 7 there? I don't know where that came from. All right, that's our answer for the definite integral. That's not our total answer for what we're doing here, right? Because there's still this 9 from f of 3. So we have 9 plus 66. So we get 75. All right, so we found f of 5 without actually knowing the original function.